All right, no intro. It's too late in the year. It's too beautiful outside right now, and I want to go for a swim. But here is the first question. Now, I kind of hope that they actually have a question like this on the test because they tell you what to do. They say make two box plots, and basically we're going to compare and contrast and all like that. Now, I'll go through this quickly because I think we know what to do. Put this into list 1 and that into list 2. Then we go to second, y equals, stat plot, and you have to make two different stat plots. Stat plot 1 will be with list 1, stat plot 2 will be with list 2. And you're going to use the box plot. I always use the box plot that includes the outliers. Anyway, then we go to zoom 9, and both box plots should show up. Okay. If you do not know how to do that, ask me on Monday. It is very important that you know how to do this. All right, now let's take a look at what they look like. So the question was talking about basically a catalyst for a chemical reaction. So this is catalyst A and this is catalyst B. Actually, just by looking at the data, it looks like catalyst B, they have much quicker times overall. But let's take a look at what that looks like with our box plots. Here they are. Now, so this is from list 1 is right here, and this is list 2. Okay, catalyst A, catalyst B. So what do they, well, the first part of the question is just do the box plot. And remember, you can press trace and get those actual numbers in there and then label that, which I would suggest. So there's that. Let's do letter B. If they were interested in making the process as short as possible, which would they use? Catalyst A or catalyst B? Well, they should use catalyst B. Catalyst B right here. All of the times, the median, the third quartile, the maximum, the first quartile, the minimum, every single one of these numbers is lower than those same corresponding numbers for catalyst A. So we would think that the reaction time is definitely going to be shorter for catalyst B, and that's the reason. All of those values are less than in this one. Now, then the next part of the question, letter C, is which one is more consistent? Obviously, well, not obviously, usually they just say, well, then it's going to be the other one, right? Well, why is it the other one? Well, it's shorter, okay? That the middle 50% is way less. That range, that interquartile range, is much less. That range between those two is much shorter. The standard deviation for this is going to be much less than the standard deviation for this, which indicates that this is much more consistent. Maybe it takes longer, but you're going to get more accurate as far as like you're going to say it definitely takes right around this amount of time, plus or minus whatever. Okay, so remember, write as much as you can. Don't assume that they can read your mind. Write it down. Assume that the person that's grading this thing doesn't really understand the statistics very well. Okay, write a lot. Now, that is question number 1. Let's go to number 2. Okay, if you read this one, you can stop the video and do that if you want right now, and then think about what we should do on this. And done. All right, so basically we're going to say, well, we think that, we should expect, let's see, 440 and 410 is going to be 850 milliliters. So we should expect 850 milliliters. But we're going to test for 900 milliliter. Okay, now this is going to be a z-score problem. Now what's going to be the new standard deviation? Well, we're adding these two amounts. So when we do that, how do we do it? Oh, right, we are going to take them and square them and add them together and take the square root, and what is our new value for this situation? And it turns out to be 0.028. Okay, now we can get started with our z-score. Basically, this is what we expect. This is what we're looking at. That's the thing we're interested in. So it should be 900 minus 850 divided by 18.028. That's going to give us our z-score, which is 2.774. 2.774. So what do we do with that? We put it into normal CDF. Normal CDF in the calculator. So when we do that, we say we want to see if it exceeds that. Let me check. Yes, we want to see if it's bigger than that. So we'll do normal CDF, and what do we get for that? So normal CDF is 0.99 what? 72323. And what do we do with this? Subtract it from 1. So 1 minus 0.99723. And whoops, what do we get? We get a very small number, as would be expected with such a high z-score, 0.00277. Okay, there it is. And that actually is the answer to the question. This is the probability that that would happen. Okay, very small probability, less than 1%. Okay, now let's do this letter B. Okay, let's start this one. Determine the probability that the amount of corn oil in a randomly selected bottle is in this blend is greater than the amount of canola oil. So if we take the corn oil, corn, right, minus the canola, in this case, if it's greater, then that number should be a negative number, right? Oh, no. I screwed that up. It's the reverse. Okay, so I got to reread this thing. Let's see. If the corn oil in the blend is greater, okay, so if we do, sorry about that, here we go. If we do canola, right, minus corn, okay. So if the corn oil is greater than the canola oil, then we're going to get a number that is less than 0. Okay, I knew something was wrong. So we wanted to find the probability of that happening. All right, now what should it be based on our problem? So the canola oil was 440. The canola was 440, and the corn oil was 410. So what we should see is right around 30. Okay, so how are we going to set this up? Ha! Z-score. Here we go. So let's see. What are we going to do? So the thing we're interested in is 0 minus what we expect divided by the standard deviation. And there it is. So let's see what we come up with. And the answer is negative 1.664. Okay, that's our z-score. So we take this number and we put it into normal CDF. Normal CDF. And we get a value of 0.048. Now, do we subtract that from 1? No, because we want to know if it is 0 or less, the area underneath the graph to the left side. So it's kind of like here, 0 and negative stuff. So that's the probability right there. And that's the answer to the question. Okay, that's the probability that that would happen. Okay, this one's a little bit tricky. Let's just say that based on our 0.048, right, that was our answer. 0.048. So that's the probability that the corn oil is greater. So the question says, what's the probability that at least one, that means 1 or 2 or 3 or 4 or all 5, right? The only other option, the complement to that is, what if none of them have more corn oil? So instead of, the easier way to say, well, why don't we just say, well, the probability that it happens is right here, 0.048. What's the probability that it doesn't happen? Subtract that from 1. So this is the probability that that doesn't happen. What if it doesn't happen all 5 times? So 0.5952, 5 times in a row to the 5th power. And that probability is 0.7819. Okay, so that's the fact that all of them are okay, meaning the corn oil is not bigger. So we would just take this, right, and subtract it from 1, and that would tell us that the probability that at least one bottle has more corn oil. And there it is. And what's the answer? Is 0.218. Okay, that was a little bit challenging. Now, let's go to number 3, or am I going to get out of here? Let me see what it looks like. Okay, take a minute to read this question. Now, can you tell from my diagram there what I'm thinking about? Now, they want to know that you know all that stuff about that. In fact, there was a whole chapter about designing an experiment. So what we're going to do is we're going to block the experiment by the breed of fish. So in other words, we're going to put 10 fish, because they tell you that you have 30 of each, right? And these are all the sockeyes. So 10 sockeye in each tank, and they get food A, B, or C. Now, you got to make sure that you weigh the fish first, and then weigh them later, whatever you decide to do. Now, that way you can determine what your results are. Also, we are going to do the same exact thing with the Chinook, 10 in each tank. And you might want to talk about, how do you assign the fish to each tank? Maybe tag the fish 1 through 30 and then somehow randomly assign them to each tank, that type of thing. And then, but I'm not sure. I mean, you might want to talk about, how do you randomly assign them to each tank and then measure the results. Now, the second part of the question was single blind and double blind, and you might be thinking, yeah, the fish don't know what's going on. But what about the people that are taking care of the fish and the evaluators? That's probably 2 different groups of people, and if it's not, it probably should be. Now, a single blind would be if the evaluators, the people who are looking at the data, they don't know which group of fish got which food. They're just evaluating the numbers, and so they don't know which one got which kind of food. That might influence them as far as how they're looking at it. And then maybe double blind would be the people who are taking care of the fish for that 10-week period. They don't know what the food is either. So they just have these random buckets of food, no labels, and then they're just throwing the food into the tank, that kind of thing. So that would be a double blind. The people taking care of the fish, administering the test, they don't know what's going on, and the people that are evaluating the test, they don't know what's going on as far as which fish got which food. Okay, so that's one way you could write that up for single blind and double blind. Okay, and I'm out.